This is the second video in the Conservation Applications of LiDAR, where we cover material presented in workshops that were funded by the Minnesota Environment and Natural Resources Trust Fund and presented by the University of Minnesota and the Water Resources Conference. Now we collaborate with the Bowser, the Board of Water and Soil Resources, the NRCS, as well as the Minnesota DNR. This is the second video in the basics of using LiDAR, where we're talking about how LiDAR works. So we need to define what is LiDAR, what is the term, and how does it work. Now LiDAR is light detecting and ranging. Basically a signal, a pulse, a light pulse, a laser pulse is sent from something and it bounces off, and we use that bounce back, that ranging, to produce a very accurate measurement. In this case, the land elevation, how high the land is, or the tree or the bush or the shrub or whatever is on the land. And this is collected with airborne survey. Now there's other ways to collect LiDAR, terrestrial, but what we're using here in Minnesota is the airborne survey, where there's up to 15,000 per second. So they're coming, lots of laser pulses are coming out of the LiDAR every second, and we're using this to collect the distance. And how we do the distance is by measuring the time. We know the speed of light, and so we knew when the bounce back comes, we know how far that is and how high we are above the ground surface. Now the light detecting and ranging is really made up of four pieces. One is the laser rangefinder, the inertial unit, the GPS, and the computer. The rangefinder sends out the signal, and this sends the signal and it gets a bounce back, so we divide it by time. So we know the speed of light, and we divide it by 2 and we can determine the time, and that would give us the distance, how high the plane is, so therefore we can figure above that reference surface, we figure that known elevation of the bare ground, the tree, the bush, the car, the house, whatever we hit on the landscape. We use a wavelength of 1064 nanometers in the near IR so that we're not hurting people's eyes if they were to look at it. And there's various different scan rates of how many signals are shot out of the laser at one time. Now the inertial unit captures the basic information about the plane and the roll and the pitch and the yaw, and we're trying to regulate that very, very carefully so it's a very flat surface that's flying. The GPS keeps track differentially of the location, very accurately, of where that pulse is sent out, so we know exactly where that elevation is located. And there's a computer that pulls all that together into a point cloud, a huge data file that shows us at these locations what the elevation is. There's millions of points. It's a very dense collection. The density is determined based on how many signals are sent out. And we're talking about 15,000 per second. And as it's flying over, scanning back and forth, it's able to support, depending on the system, down to sub-foot to 2-foot contours. So very detailed elevation information with about 1 to 8 points per meter. And we have validation methods to check this, to control that, so we know exactly what is being collected. Now the end product is a very accurate registered X and Y elevation for each data point. So every meter we know how high it is above that reference surface. And sometimes it's how high it is whether it's hitting a building, whether it's hitting a tree, or whether it's the bare ground. And there's several different products that are derived from this laser point cloud and provided as with this service. One of which is the DEM. Others are contours and hydrological break lines that help us process these more accurately. Now, this is an example of the very, very detailed contours that can be produced from this 1 meter base product. The LiDAR returns multiple measured discrete returns, multiple discrete returns. So when the signal goes down, it bounces off objects, and it can bounce off a branch or the grass or the ground, and we classify these. And all this is written up in the metadata, so you can read about it, but we calculate the discrete pulse as it return in the pulses as they return in discrete units. And we also measure the strength or the intensity of each of those pulses. So we're able to use that to classify what the LiDAR is hitting and how high it is, or the elevation. So here's an example of return. So the LiDAR shoots down from the plane, it hits a branch, it hits the bare ground, and there are single returns, there's multiple returns. There's also another type of classification, and that is the waveform, and we'll talk about that in a second. So basically the signal comes down, and the first return hits the highest thing, and it could be the bare ground, but if it hits a tree, it could penetrate a little further to the lower branches, the further lower branches, and all the way to the ground. So there's a first return, which could very well be the bare ground if it's in an open area, or the first return might very well be a high part of a tree. So there's these discrete returns that are being classified. Now, when this laser pulse comes down, we actually have we classify this into discrete returns. We call this first return, this second return, this third return, this fourth return. And each of these returns have intensity, the strength at which it's returned. But we could classify this entire waveform structure to help us obtain even more information. Now, that technology is not what we're using here in Minnesota for our products, but that is another aspect of LiDAR analysis. So it's discrete returns or multiple returns, or this waveform analysis, where you're collecting a lot more, you're processing a lot more information as it's moving up to that pulse and coming back. Now this is an example of what's collected from LiDAR. Here we're hitting the ground, and you can see the contours here, the bare ground, and it's also hitting branches, and we're able to use this to figure out the height of the trees. Now we've colored the trees a little differently. The very tall parts are red, the next levels are yellow and blue and green, so we get an idea of how the canopy, but some of the LiDAR penetrates all the way to the ground, and we're able to then get a bare ground surface. So there's multiple pieces of information we're getting on the returns. Now, each return has an intensity, and we're able to use that intensity for other products. And the intensity is determined to some degree by what it's bouncing off of, because water absorbs differently than vegetation. And that when we're looking at intensity, it looks very much like a IR product. Now, the Minnesota DNR data was started quite a few years ago, where we had a series of projects collecting information in areas of the state, the Red River or various DNR products. There were some other communities that got involved in the early days, and we created the Governor's Council on Digital Elevation to try and coordinate this. We weren't able to receive state funding in those early days, so we worked with counties or various different individual projects to develop our expertise in LiDAR. But with the Clean Water Amendment, the Clean Water Fund, the Legacy Amendment, we were able to receive $5.6 million in funding led by the DNR to collect statewide LiDAR. And this was done in partnership with the USGS and the the EPS, and as well as MnDOT and MnGeo and local and county governments. So it was a partnership of many different entities, and that from the Elevation Committee that we were able to develop the details of this analysis process. And the details were set up with a series of standards that were established based on the accuracy that we wanted to derive for this statewide collection, both the horizontal and the vertical accuracy, and the coordinate system that would be used for this, the reference, so that we'd be able to match it up to other layers, data layers that are commonly used. Now this began in 2011 and moved through 2012. And it's pretty well statewide available at this time. That you can receive this information from the DNR or the MinGeo. All this information is carefully coordinated with the National Digital Elevation Program, where on a national basis we are building an elevation model for the entire country. Now this was done from 96 to 2011 over a series of efforts, and the key issue was to create a seamless elevation model across the entire U.S. because early collection was done in different projects, and there was issues of overlap, and that we tried to create a seamless product across the U.S. So we're part of a larger effort to create a U.S. Seamless digital elevation model. Now, what's available and what's not? You can, from the information that's collected from the Legacy Amendment funded data, you can get elevation data that shows bare Earth, and then that bare Earth information was used to derive a digital elevation model at several different resolutions, the 1 and 3 meter. And there were also hillshades and contours and tins that were created. And there were some hydro brake lines which were used in this processing. And then obviously there are buildings that were pulled out of this data, so that this information is available for you. Now you've got to calculate this. You've got to use GIS skills to calculate some other derived products, the slope, the stream power, the flow accumulation, and to also correct this, to hydrologically correct this product. And we'll be discussing this in later videos. Now, how the points are classified. So the pulse comes out of the airplane, bounces back, and we calculate that location, and we're able to classify that into bare Earth based on how it's returned and the intensity of the return, and into building or car or bridge, various different objects. It's basically bare Earth and building and then vegetation and water. And this is all developed from national standards. The American Society of Photogrammetry and Remote Sensing developed these standards, and we implemented them here within our state application of LiDAR. So we classify the points within a certain level of accuracy, and we have an automated classification. But the manual classification is also a process that it is used to tune up or improve this. Now, the manual is the time-consuming part of it. So there's a automated classification that gets you most of the way there, and then there's a series of manual classification that is done within these products. The vertical accuracy is validated so that we can make sure we got what we paid for. And we also want to have a high level of integrity. So we go through an elaborate validation. When the vendor produces this, flies over, collects the data, classifies it, that we go through a validation and integrity process to make sure we know what we've got and we know how to use it. And to do that, we compare the information that was flown with surveyed data that we've collected in each of the study areas. And we have points collected in 5 different cover classes, and we work with the county surveyors to collect this. So it's an elaborate validation process that go through. Now, the error and accuracy of this is determined by this process. Determining the value of this data is very important that you understand the accuracy measurements that were used in this process. The 2 that were used were the NSSDA and the National Map Accuracy Standards. And these 2 are comprised of several components. Here's a comparison of the 2. The NMAS is a contour interval equivalent. The NSSDA, we have an RMSE component and a 95% confidence factor component. But these are the two national standards that were used in our accuracy calculations. Now, when we calculated the accuracy, we had to have ground truth or validation points. And we collected these level ground, away from breaks, flat ground, very, very clear, good sites. We collected the elevation and the GPS information at that location. And we also classified it into cover class, where we were, whether it's open terrain, whether it's tall grass, brush, forest, and urban. And our accuracy was put together into two pieces and then consolidated. The fundamental was the best case analysis, and the second was within our cover classes, and that was all consolidated into a combined accuracy or consolidated accuracy. Now, since the laser measurement doesn't fall exactly on our survey point, we had to do some interpolation. So we took the nearest laser measurements and we interpolated a surface so that we were able to get a good calculation of what the laser measured at our survey points. So that from these actual laser points, we interpolated it and we compared it to our 371.93. And our interpolated value is what we're talking about for the difference here, to say how different is the laser, the LiDAR value compared to our ground truth measurement. And we did this all throughout Winona County. In this example, the little triangles at these points we collected in all those classes, and we compared our data. Now, the comparison in the NSSDA component, it's important to understand there's an RMSE and there's a 95% confidence factor. We go through a calculation to measure the RMSE, and then after we've calculated the RMSE, we multiply it by, assuming a normal distribution, that we multiply it by 1.96 to get a 95% confidence factor. And here's an example of it. So from all these points that we measured on the ground and compared to our interpolated LiDAR measurement at that same place, we have an RMSE of 1.61, and the overall confidence factor at 95% would be at 0.315. So it's basically at 16 centimeters our RMSE, and at 32 centimeters is our 95% confidence factor. So it's very accurate information. Now the RMSE, breaking it out by cover type, you can see that in the brush and in the forested and tall grass, it's a little less accurate than the open, but you get an idea of difference between 12 centimeters to 19 centimeters. It isn't that large. This is the vertical error distribution report that's included in the county validation report. This is Winona County, for example, and you can see the different classifications. Remember the land classes we talked about. And this is elevation on the x-axis, and here's error on the y-axis compared to our ground truth point. And you can see here's the trees, here's the bare ground, and you're getting an idea of how the error is distributed. Now the error, when we compare it to national standards, you saw the overall was 16 centimeters. You can see that we're well within the standard of the 2-foot contour intervals, either determined by the NMAS or the NSSDA. These standards you can read more about at the USGS site. And understand a little more about accuracy standard specifications. Now there's a couple of things to wrap up this video that are how LiDAR works. You want to remember LiDAR can measure all sorts of different ground surfaces and things on the ground, but it can't penetrate water, at least the LiDAR that we were using, the near infrared, the 1064 nanometer LiDAR. There is LiDAR that can penetrate water, but we used the near infrared. There's difficulty getting through a heavy canopy. A little bit gets through, so we're able to use it, but the heavy canopy is an issue. We avoid the rain and clouds by the time we fly, but that's an issue. And there's also issues of the timing of a limited window, or whether it be flooding, high winds, or snow-free. So there are some mechanical issues which we have to consider when we're collecting this information. This ends this lecture.